Ladies and gentlemen, welcome from Düsseldorf. Welcome from the AMI, Fire Resistance in Plastics, and also welcome to the European Fire Safety Week. And we're broadcasting here live from Düsseldorf, from the Radisson Hotel. And the next session, that is the session that's part of the AMI, Fire Resistance in Plastics Conference, and in parallel also a session within the European Fire Safety Week. This session has been organized by PINFA, the Association for Non-Halogenated Phosphorus, Inorganic and Nitrogen Flame Retardants, and we're proud to be a partner to the European Fire Safety Alliance, who have started the series of European Fire Safety Weeks some years ago. This is, I reckon, the fourth European Fire Safety Week, and it used to be an in-person live event in Brussels with a lot of personal interaction. As we know, due to COVID, this is now severely limited. We're lucky enough to be able to be here in a room in Düsseldorf for the AMI conference, and because of the time overlap or coinciding timings for both the conference and the European Fire Safety Week, we tried to merge the two events. So, in the next hour and a half, we'll see a few presentations, and on the screen, you see our speakers. We have a good lineup of renowned, respectable experts in fire safety who will talk about the challenges of fire safety for new energy systems, particularly for buildings. We have addressed as PINFA in the past a lot the challenges of new energy vehicles. We have had specific special webinars and online events related to electric vehicles and their fire safety, but today we want to look at buildings and in particular to photovoltaic systems and related installations. So here on the screen you see our lineup of speakers. We have Victoria Hutchinson from the Fire Protection Research Foundation. We have Victoria joining us from the US, Eric Guillaume from France, he works for Effectis, Alexander Kushner from Currenta Fire Technology, not far from here in Leverkusen, Yoon Ko from the National Research Council of Canada, and here on stage with me are Corinna Neumeister and Kazuo Ninomiya, who are colleagues from PINFA and also experts in fire safety, and they will also engage in the discussion later. With that being said, you find here in the room, for the audience here in the room, you find on your table this QR code. If you want to scan that, you can join the online Zoom event and use that for participating in the chat. So asking questions via chat, also maybe having side conversations on the chat. If you have very specific questions, that is an option. If you do that here in the room, please just make sure you mute both microphone and speaker so we don't have any interference with the audio here in the room. But otherwise, you won't need it for following the debate and the discussion because that's all going to be here upstage and on the screen. So that's just to the QR code that you find there. So without further ado, I'd like to announce our first speaker, and that's Victoria Hutchinson from the Fire Protection Research Foundation. She's a research project manager there, and I hope, Victoria, we have you online.
Yes, I'm here. Thank you.
Excellent, very good. So over to you.
Perfect. Thank you, everyone. It's a pleasure to be with you today. I wish I could be there with you in person, but I guess given the conditions, we'll have to settle for virtually today. But I'm excited to share a brief overview of some of the fire safety challenges of new energy systems, independent energy systems, and then energy systems in the context of buildings and what we're seeing in terms of materials for energy efficiency. Some background myself, as he said, I'm a research project manager with the Fire Protection Research Foundation. A lot of my work focuses on emerging technologies, renewable energy, a lot of battery energy storage, photovoltaics, energy efficiency, things of that nature. First got involved with energy storage work back in 2011, and it has been a large portion of my focus since that time. So pleasure to be with you today. So we'll go ahead and get started here. So over the last decade, going green has really become increasingly mainstream. In an effort to use less energy, save resources, and reduce pollution and waste, we're now embracing these alternative energies supporting energy efficiencies, and practicing recycling. But it's important to recognize that going green isn't just about electric vehicles or solar panels or battery energy storage. It's also about buildings, because structures are a very large consumer of energy. Let's see, I don't seem to have option to move forward. Oh, there we go. So population growth and urbanization are two of the largest drivers behind green initiatives and new energy sources today. The world's urban population has risen sixfold since 1950, with over half the world's population living in cities. The world's cities occupy just 3% of the Earth's land, but account for 60 to 80% of energy consumption, around 70% of global carbon emissions, and over 60% of resource use. So this rapid urbanization is exerting pressure on our global resources. So it's now recognized that these buildings, they need to be more sustainable, energy efficient, and disaster resilient. So in response to societal objectives, there's been substantial investment globally in clean energy, energy efficiency, and all of this has driven new innovations, including development of new products and systems to make buildings greener and more sustainable. But as a result of this dramatic investment, these systems and materials are proliferating at an exponential pace, as we all know. So here's just a quick snapshot of what attributes make a building green. These green building materials, systems, and features are collectively referred to as the attributes of a building. And these can range from the interior materials and systems to exterior materials, systems, and facades, all the way to alternative energy sources on site or electrification infrastructure on site to support electric vehicle use and other items. So some of these new materials and energy systems, they're constantly being developed. We recently published a study at the Fire Protection Research Foundation on the fire safety challenges of green buildings and attributes. And in that study, we identified over 100 green attributes that are now being incorporated into modern building designs or physically on the building site. So here on this slide, I've provided a representative sample of some of these key trends in these categories. So starting with the site, we're seeing a lot more presence of electric vehicles and other alternative fuel vehicles. We're seeing a huge surge in dockless electric bikes and electric scooters, which all are battery powered. We're seeing a huge rise in densification just in terms of what is on the site. That also poses challenges to the fire service in terms of access. And some other things, the building systems, we're adding a lot more infrastructure for electric vehicles and our alternative source vehicles. We also are putting new energy sources on site. So battery energy storage systems, photovoltaic panel systems, or building integrated photovoltaic systems. In the structural materials and systems, we're seeing, more lightweight engineered lumber systems, mass timber construction, additive manufacturing, such as 3D printing, a lot of things that are changing these structures and materials to improve energy efficiency, improve resource use, the ability to recycle materials, etc. We also have exterior materials and systems that support energy efficiency, such as facade and wall systems, timber facades, organic insulation types. Then you have your facade features as well, so that out of plane geometry, solar radiance, the area of combustible material, and things of that nature. So these are some of the trends that we're seeing, all in support of getting new energy sources on site, having more energy efficient buildings and more sustainable facilities. So what does this mean for fire safety? While we're fully supportive of green building products and systems, the fire safety community has been increasingly worried about the impact of these emerging products and technologies on fire safety. So recent fire incidents indicate that the adoption of these systems can sometimes have unexpected consequences when the safety considerations are not considered early enough in the development phase, or when unexpected combinations of materials are used to create and install systems outside of their original specifications. So having fire safety take a back seat to other performance parameters and buildings isn't necessarily new, unfortunately. But fire safety always seems to be playing catch up with developments occurring in the construction industry. So even when, we as fire safety professionals are aware of potential problems or concerns with new technologies, it oftentimes it has to wait until there's some type of incident before the issue starts being addressed holistically. But here I'm going to walk through, some of the fire safety challenges that we're seeing in some of these new energy systems that I showed on the last slide, and some of these green attributes of modern buildings today. So starting with the site, as I mentioned, we're seeing a big rise in electric scooters, electric bikes, and other small battery-powered devices are becoming more common at both residential and commercial sites. So charging lithium-ion batteries for devices like scooters and e-bikes, we found in the US between 2015 and 2018 that there was around 330 fires in these types of transport mechanisms. This caused more than 9 million in property damage, according to the CPSC. And last year in New York City alone, they had 44 electric scooter fires that resulted in 23 injuries. So they're on pace to double that number this year as they're becoming more and more prevalent in cities. So when you look at this image here, this is a apartment fire that burned down as a result that was sparked by a scooter battery. So, the impact, even though it's a very small battery, very small kilowatt hour, it can have a pretty significant impact. And we've seen this in others for, the battery has exploded and caused a lot of damage in hotel rooms as well. We're seeing people take these and charge them in their homes. So, the uses of these are changing pretty drastically in terms of where these batteries are being taken. So next, with building systems like the EV charging infrastructure, this can present an ignition hazard while charging. We have seen some incidents of this, but there are a lot of proper mitigation strategies that are in place, like adequate shutoffs, shock protection, clear signage, etc. And with all of that taken into consideration, they're generally considered a fairly low risk, but there is more research and testing needed to further quantify their contribution to the fuel load or the fire risk. And we do have an active project underway at the foundation looking at electric vehicles and charging stations, particularly in parking garages and dense settings as well. So going into battery energy storage systems, they're a very critical part of today's dramatic push for sustainable and renewable electrical energy, as they provide that means of being able to store the energy that's produced by other sources. So since 2018, there's been over 40 incidents in these large scale systems like you see here in this image. And then that's around the world. And of those, all of them have resulted in some form of failure, resulting in either a fire or explosion. So far this year, there's been 8 incidents in 2021 that have impacted a combined energy capacity of around 1.7 gigawatt hours. So pretty large scope there. But while there's a variety of battery technologies used, lithium-ion batteries are the most common technology at this time. But we are starting to see a lot of other technologies gain some traction. But the lithium-ion batteries do present a pretty unique challenge from a fire and explosion perspective. And while there's a lot of research being conducted, in this space on this technology, and we are making a lot of progress, there's still a lot of unknowns and challenges with respect to these systems using lithium-ion batteries. From controlling or stopping thermal runaway, all the way to finding an effective suppression solution, to establishing proper response tactics to these incidents, all the way to the decommissioning side of things and dealing with the stranded energy hazards and delayed ignition behavior. So next, PV systems. I know you're going to hear quite a bit more about this today, so I'll keep it brief, but they can present an ignition hazard and can contribute to the fuel load. Largely the percentage of these incidents with respect to the number of installations is fairly low, but they can present a shock hazard to firefighters. And research indicates that some indication that for roof mounted solar panels, the space between the roof and the installation can create a flue-like condition, accelerating the spread of the flame. So In this case, the size of the space and angle of incline are very important parameters to identify the fire risk of this installation. But there's a lot of research going on in this space, so I encourage you to look into that. Next one is, regarding facade features and exterior materials and systems. So adding insulation to buildings really impacts how a fire can develop within the building by keeping the heat in. Airtight buildings increase this effect and can produce pressure differences inside the building, which can pose a escape hazard and also challenges for rescue. And many of these new construction products are combustible and can potentially feed the fire. So the Grenfell Tower fire in 2017 really brought this concern of combustible exterior walls and cladding systems to the forefront. And we've done a lot of research on this at the foundation. I know there's a wealth of other resources on that as well. And the final thing is, structural materials and systems. This has changed a lot over the years. We use lightweight engineered lumber, plastic lumber, mass timber, cross-laminated timber, and all of these can present additional risks when compared to traditional building materials. They burn readily once ignited and can contribute to the fuel load and increase the heat release rate. So there's a potential for a shorter time to failure, along with concerns of stability, flame spread, and fire department access. So that was just to provide a brief overview. And all of these, are attributes kind of make a building green. But the important thing to remember is that if it burns down and needs to be reconstructed, that's not necessarily green, right? So keeping fire safety at the forefront and making sure that we have all the testing methods and all of these things and standards in place to protect them from the forefront is essential to being able to carry this forward. So with that, thanks for your time and attention. We've done a lot of research on all of these topics that I briefly covered here. Those are all available at nfpa.org/foundation. And I provided a couple other specific sites related to our research on energy storage and PV systems if anyone is interested. So thanks so much for your time, and I will hand it back over.
Yes. Thank you very much, Victoria. Was a very nice overview and also introduction for the following two presentations, which will dive into more in detail into the topic of photovoltaics. And I didn't mention in the beginning, we have a set of 3 talks, Victoria and the next 2. And after that, we have a Q&A session, then another 2 brief presentations, and after that, again Q&A. So keep your questions for this first Q&A session we have after the next talk, or the talk after the next. So it's my pleasure to now welcome Eric Guillaume. Enchanté, Eric, to hopefully see and hear you again. Eric is very well known in the fire safety world. He's been very active over the last many years in standardization, also environmental aspects of fire testing, and he will talk to us about fire testing of photovoltaic systems. Good to see you, Eric. Welcome. Hello. We don't hear you yet.
Oh, yeah. Okay. Thank you, Adrian. Sorry, I think I cannot reactivate my microphone myself. So that's why I hope that you hear me.
Yes.
Yeah.
Yes, we do.
So welcome, everybody. I'm very happy to present you the photovoltaic systems in building aspects on regulations and testing related to fire safety in Europe. So it will be a very short presentation, but give you just an idea of what exists for that. So first of all, we have to start by definitions. And when we deal with photovoltaic systems in building, we have to deal with 2 different kinds of products. They are defined in an harmonized EN standard, which is EN 50583 parts 1 and 2. And in fact, we separate what we call BIPV, which is building integrated photovoltaic modules, to BAPV, which is building attached photovoltaic modules. And on the picture you see on the screen, you have BIPV tiles on the roof. So it gives you an idea, it's totally integrated. and it's really different from the BAPV, which is put over the building. And so what is important will be the interaction between these different products and the envelope of the building. BAPV are defined as providing a function that is in the framework of European construction product regulation. So it's very important because it means that they have a function that is important for the building. It could be mechanical function, it could be fire protection, it could be noise protection, and so on. So you have a list of essential elements. But what's important is really to think that BIPV is part of the integrity of the building's functionality. So if you have to dismount a BIPV module, then it would have been replaced by another building component because it's really a part of the building. In contrary, BAPV are defined as mounting over a building envelope. So it could be facade, it could be roof, and so they are not integrated really. And in this case, you have a picture just that show you the BAPV module on a tile roof. Next, we have to discuss with ignition scenarios with PV modules, even BIPV or BAPV. So this is an electrical system, so you have to respect the national electric codes that are in place in the different countries to limit the overload and short circuit. But all this part that is called smart grid is sometimes difficult to manage because it's a direct current. It's not necessarily alternative current. So management systems are a little bit different. Then we have two families of sources of fire, the internal sources to the PV components and the external sources. The internal sources cover the arcing hotspots, but also some other very specific effects to PV cells, which are called mismatch. And it's a question of misalignment or reverse current in a module. So you could have, for example, when you have a partial lighting of a PV panel, you could have such kind of effects. And you could have also lack or bad connections among modules, strings, and inverter that could generate also weak points for the start of a fire. The external sources include all the classical building fires, so such flames that are impinging on the facade from windows, but also on roofs. And you could also imagine external fires, such for example, a car that is burning in the front of a building, or fires from wildland areas, and how does it work at the neighborhood. In this case, the combustion or the ignition could be made by direct flame impact, by radiation, by convection, and sometimes by firebrands also, which is an important point, especially for the photovoltaic systems that are close to wildland areas. The performance requirements could be divided at module level and at system level. At module level, we have panels that may have to comply to EN 61730 Part 2. And this standard describes several tests, including fire tests, and especially MTS 23, which is a test that is requested only by the manufacturer. So it's not mandatory, but the test itself is based on UL 790. And you will see a little bit later in my presentation, it's very similar to the other roof tests that we have around the world. So, but what is important is that it means that you have very few harmonized set of requirements, but it doesn't mean that you have no local or national building codes that integrate requirements on PV panels. At the level of the product, the series EN 50583 requests Euroclass level E, meaning a small flame on the different components. I mentioned that because very often on the market, we don't see necessarily the evidence of test for that, and especially of the impact of the small flame on the different locations. And there are a lot of different locations, including the back and so on, that matter. In some cases, especially for BIPV panels, they are also a part of the envelope of the building, so they have to meet the requirements we have for this envelope, which may be fire resistance test or roof tests. We have a series of specifications like that, but as you probably know, the specification is not harmonized for roof at present time. And we have several also product standards. I mentioned the one that is considering BIPV glass in facade that already cover fire resistance test according to EN 13501 part 2. So, and really a classification that is a fire resistant one. And other provision for sure may be included in local or national building fire requirements. So I just give you some examples of the tests that are applied on photovoltaic systems. So here it's a BAPV system, and the test is following a standard that is CLCTR 50670. Normally the test is done on a dummy inert roof, but here it has been a little bit different and applied to see the interaction between a roof complex and the PV module, because for sure there's a strong interaction between both components. And so in future developments or future needs to understand the fire risk, we have to integrate the interaction between the photovoltaic panel and its substrate. Here, these are examples of determination of Euro classes for PV panels. So on the left, you have a small flame that is impacting cells. So this is how I mentioned that we determine this E class for the panel. So we put the small flame at different locations, including different plastic elements, and on the front and on the back, and so on. And on the right, it's SBI test performed on PV panels. And this comes from certification rules that are available for France. And the last one I give as an example is roof test according to TS EN 1187. It's a test free, the French test, and there's a French protocol that is available for that. And in that case, you have firebrands plus radiation plus wind, and you have a protocol that is standardized. And here, in this case, it's photovoltaic panels that are BAPV and that are mounted on roof, but it could be the same test for BIPV also. And so it gives you an idea on how we could test such kind of panels. So normally we have to fulfill these different requirements on the market, but very often there's still work to do for the control and so on. So it gives you just an idea of what is the existing requirements that we have for these photovoltaic panels, and I remain available for more questions or details during the roundtable. Thank you.
Merci beaucoup, Eric. Yes, it looks like a lot of work has already been done on fire safety of photovoltaic panels, and also standardization has engaged in that topic. And we've continued with this topic with Alexander Kuchner. He's from Currenta, a test house, fire test lab, not too far from here in Leverkusen. His background is fire safety engineering, and he graduated from the University of Wuppertal, where many years ago I also gave lectures on fire safety and flame retardants, by the way. So over to you, Alexander.
Hello, everyone. My name is Alexander Kuchner from Currenta Fire Technology. I welcome you to my presentation about fire testing of the fire risks of standoff PV modules on the roof structure within the European Fire Safety Week 2021. First of all, I will give you a short introduction into my presentation, followed by the test setup, the test results, and at the end, I will finish with a conclusion. Roofs in Europe are tested and approved for specific scenarios, including, for example, external fire impacts. But what happens to already approved roofs on which the photovoltaic or PV system has been installed under the influence of external fire? Due to installed elevated PV systems, a different fire behavior of the roof is present. But the question is, how big is the impact? The current recommendation from insurance companies is not to install PV systems on roofs with combustible insulation. We are now going to take a look at the test setup. In this image, you can see the tested PV module with the fire source, gas burner underneath, which are placed on the roof structure, in this case a hard roofing according to the criteria EN 13501. The test setup is based on the fire test standards for roofs following the CEN TS 1187 test method 1. But instead of the fire source of wood wool, we have designed and used a square gas burner. This has proven to be a suitable ignition source during the experiments and produces a thermal exposure similar to wood wool, but has a more constant heat release and is more reproducible. The aim of the experiment is to investigate the effects of external fire exposure on both the roof structure and the PV module. In this context, the PV module represents an additional fire load and prevents also the heat flow to a certain extent, which leads to an intensive thermal load on the roof structure. On the next slide, you can see the test results of two comparable roof structures with different insulation types. The first point shows the test result of a class A2 insulation according to EN 13501 with a mineral fiber insulation material. The second point shows the test result of a class C insulation with a thermoset foam insulation material, also called PIA insulation. The middle image shows a flame spread during the test, and the right image shows the test result and the damage of the insulation after the test. On this picture, you can see the burned PV module at the end of the fire test, so after 10 minutes. It can be clearly seen that the PV module is completely destroyed. In this case, the plastic backsheet being the major contributor to the fire. And you can also see on the roof that the upper bitumen sheet has partially melted. To sum up the main points, it has been shown that the use of the square gas burner as an ignition source provided a constant heat release and better reproducibility in comparison to wood wool. The damage pattern on the insulation materials is comparable. None of the tested insulations contributed significantly to the fire. In general, the performance of different PV modules differs from each other, depending on the design and especially the materials used. In conclusion, I can say that for the safe implementation of the energy transition, the fire protection requirements for PV modules have to be re-evaluated. Now we are at the end of the presentation. It was a pleasure being here today. If you have any questions, feel free to ask them. Thank you.
Thanks a lot, Alexander. Thank you very much.
Hello, everyone. My name.
Okay. Okay. Good. Now we have a good 15 minutes for Q&A. Are there any questions to the presenters here in the room? And I trust you, Chris, have followed the chat, but let's, perhaps while we're waiting for the room, are there any questions from the chat that you would like to highlight?
Not from the chat. There are some questions that there's one question I had to the particularly to Alexander and Eric, have you also been testing the cable systems, the inverters? Do they represent a fire hazard, or is it only the panels?
No, we already tested all the different components, including the cables and also the connection boxes and so on. This is also a weak point of what is not fully regulated at present time. As I mentioned, if you take the national electric codes for different countries, very few are familiar with DC current. And sometimes this is where you have also a risk because they are not fully considered.
So I think all three of you are saying that standards need to be updated, things are not fully regulated today. And Victoria, you were saying the regulations are kind of running behind innovation in construction. How can we change this rather concerning situation? How can we push regulators to see that we need to take things forward for these new energy systems?
I think that's definitely a challenge. It's, it's something that we've been struggling with, for quite some time. But I think it's the fact that we need to ensure that as these innovations and new technologies and everything is being developed, we need fire safety in the conversation at that point in time, because in the codes and standards process, the reason that it becomes delayed is they feel like there isn't adequate information at that time to make decisions that can have such broad impact, right, across the country or across the world. So I think it's the collaboration that we need to be able to share, testing results, share research, and then be involved in those conversations as things are being developed, so that the codes and standards writers can have information that they feel, confident that they can make decisions on. But it's definitely going to be an ongoing challenge.
If I can add, for the case of PV panels, I think we have all the tools to test them. What we have not at present time is necessarily the implementation in the different regulations, because sometimes people are not very aware of how it works and what is the real risk. We mentioned the interaction between, for example, the roof and the panel. We could mention also, we have also rules that we didn't present it here about interaction with firefighting activities, for example. So you have different things that exist, but many often it's a question of education. People are not aware enough of the risk so that they cannot regulate properly. I will say there are good and bad panels. Manufacturers are not very pushed to make tests. So sometimes it's a question of insurance company, sometimes it's a question of building owner, but we have this weak point in the regulations in many countries at present time.
Yes. Perhaps a question to Alexander, because you highlighted the roofing material. If you have photovoltaics installed on an existing roof, and the two materials, two samples you tested, one was the mineral wool, and the other was the thermoset, the polyisocyanurate, the PIR. So I think in terms of flammability or fire behavior, very benign materials. What about, or what would be your expectation if you had something like polystyrene insulation there, or more flammable, so not class C, but a worse class in the European system? Have you looked at that as well?
No, we don't have done that, but I think, in this case, we need more research work, and maybe, I think as you can see in the test that we done, we enveloped a new gas burner because the wood wool is in a basket, and the dimensions of this basket does not fit directly in the corner under the PV panel. So I think, we have to do more research work for that. And I saw another question here in the chat. In case of a fire, the insulation falls down. What is then the fire protection of the building? I think that the roof has to be in any case hard roofing, according to the EN standardization. So I think, yeah, in that case, the house burns down.
Okay, thanks. Yes, we have a question here in the room. Just hang on.
Hello, everybody. I'm Peter Mapleson. I'm a technology editor with Compounding World magazine. First of all, a question for Guillaume. I mean, I don't want to trivialize this, but the fact that photovoltaic panels are located on the top of a building, on the top of a house, is this taken into consideration when it comes to regulations? Because if the panel actually catches fire, the heat will rise. I don't know how much danger there is, risk there is, of the heat of the fire actually being transmitted downwards into the house.
In fact, it's not so simple, because more and more we see projects where we see more and more glazed parts of the facade that are covered from PV panels from the ground to the top, and sometimes with very high buildings. So we saw in some countries that it has been considered as accessories, so it was not requested to comply with the local facade performance requirements, for example. So things like that. So I will say it's not so simple, but you're right, the fire is going up. So if you have a fire on the roof, it's not necessarily penetrating inside, but that's why also the importance of the interaction between the roof and the panel is very important and has to be assessed. Right. When we saw the B-roof tests, even if it's whatever of the 4 tests, we look each time at the propagation, but also at the penetration of the fire.
Right. So maybe you need different regulations for panels on roofs and panels on sides of buildings.
Yes,
just a thought. Question to Alexander. I'm not quite sure who it was that gave this advice. I think it was an insurance group saying that it is their advice to not mount photovoltaic panels on roofs with combustible insulation. Is that right? Did I get that right?
Yeah, that's the case.
Okay. So what is not combustible? What insulation is not combustible? I mean, if we take the unfortunate Grenfell tower fire, materials supposedly non-combustible and yet went up like candles. So one could reach the conclusion that you better not put photovoltaic panels on any insulation at all.
I think that the insulation types are in different classes. So, like, for example, mineral wool is a non-combustible insulation, or partly non-combustible insulation. And like the pier insulation that I found in the picture, that's a typical, I say, combustible insulation. But I think you have to differ the insulation types and, have to look what the test result is in any case.
I totally share the what Alexander said. We have to have evidence of testing before deciding. So you cannot presuppose that a product will perform or not. You have to test it to know. And here you have to test it at the product level and not only the materials that are used for it. So you have to have the interactions. You have to have the case, the casing, the cables. Everything are elements that matter for the fire behavior of the PV panel.
Okay, thank you.
Yes, perhaps coming back to Victoria. When we look at photovoltaic systems and renewable energy, which has the disadvantage that it's not available constantly. Yeah? The sun only shines during the day, wind is not around, it's not windy all day, all night. So we need storage systems. Yeah? Will we in future also have more electrical storage system in houses, not only maybe private dwellings, but even office blocks, buildings. So this whole area of energy storage in buildings and maybe huge batteries, do you feel that that is sufficiently addressed in terms of fire safety?
I would say this is a very active area of research, right? We're seeing quite a large increase in installations around the world in the US and other countries as well. As you said, when the sun's not shining and the wind's not blowing, right? This gives us a means of storing that. So that's gaining a lot of traction, but there's still a lot of questions. There's a lot of variations in the technologies and the chemistries, which all have different behaviors, the installations, all, from different manufacturers and integrators. There's a lot of variables there that impact the fire behavior. And then just the nature of lithium ion batteries in and of themselves, the challenges with thermal runaway. There's still a lot of questions that we don't have answered. I know the incident that we had in Surprise, Arizona, that we had an explosion, that actually it raised a lot of questions in the research community about the off-gassing from these batteries and the proper design and protection. What, if we have a gaseous suppression system in there, does that actually increase the risk for an explosion if it stops the burning but doesn't stop the reaction and allows continued off-gassing? So this is a very active area of research at the Fire Protection Research Foundation, and I know a lot of others across the world are doing a lot of work on this. And Dirk Long, I believe you'll hear from later at FRiP, they're doing a lot of work as well. So there's definitely still a lot more questions than we have answers, but there has been a lot of progress. There's a new NFPA 855 standard for energy storage systems, which is being utilized, and that's going to help carry us forward as long as tests to evaluate the fire safety performance, such as UL 9540A. So we're making a lot of progress, but we're going to continue to see them deployed in residential settings and commercial settings and utility settings. So there's still a lot of work to be done, but we are definitely making progress.
Yeah, thanks. Any thoughts on this from the European perspective, Eric or Alexander?
Yeah, it's a very good question because, as I mentioned, one part of the problem in Europe is that PV could be considered as a construction product, especially for BIPV, but at the same time, the compliance is at the building level, and so it's nationally regulated, and the building envelope is nationally regulated. For the case of facades, and BIPV and facades, at present time we are working on the European harmonization. So it will take several, I will say, years to issue a final harmonized standard for that. But and after, I will say it's more political than technical. As I mentioned, we have the tools to test. So we have to have the right regulations and also the right implementation of the regulations. One part of the problematic is really to be able to consider these products in the projects, even if they are put on place a long time after the construction. So it makes another difficulty.
Okay, thanks very much. All right, I think we should move on then. I see also in the room here no hands raised. So thanks a lot so far. You're welcome to stay, Eric, Victoria, and Alexander, for the rest, of course, and also ask questions later or join later in the discussion if you like. But we come then to our next set of presentations, two presentations that we still have, and I realize here is one name missing on the slide. Apologies for that. But we now continue with Yoon Ko from Canada, from the National Research Council Canada, and she leads there the Fire Research Lab and Group. She's also an adjunct professor and has long experience in fire safety research. And I hand over and across the Atlantic again to you. Yes, Yoon Ko, please go ahead.
Thank you. So I'll share a review of fire safety of photovoltaic system in buildings. My control is not working. Can you move to the next slide, please? Thank you. So With advancements in PV technologies, PV modules are, as we know, that's integrated into building skins and turn them into solar cladding, solar glass walls, solar skylights, solar roofings, and so on. And these solar products not only generate electricity, but also consist of buildings. Next slide, please. So what makes the BIPV products more vulnerable than other regular building material is that the fire can originate from the BIPV for physical causes like cell damages, cracks, for environmental causes, shedding, dust, moisture in grass, and for electrical causes, hot spots, arc, and so on. In victim scenarios, BIPV can catch fires by being exposed to external fire sources, arson incidents, and so on. So fire risk of BIPV should be addressed for especially electrical safety of PV modules to prevent the fire originating from the PV modules. But more importantly, for fire resistance of PV products as building components to limit the fire spread to the buildings and the neighboring buildings and to allow safe egress. However, BIPV standards do not provide PV-specific fire resistance requirements in detail yet, but they refer to local building codes. As Eric mentioned, that's, for example, EN 50583 refers to EN 13501, which is actually developed just for the normal construction products and building elements. So next slide. So PV modules, as we know, that's made of multiple layers, top protective layer, often glass or plastic, and encapsulants, solar cells, and back sheets. So these encapsulants, like the EVA, is reportedly the main combustible components, and some back sheets are known to be flammable as well. So construction materials are required to be evaluated for their fire behavior, combustibility, ignitability, heat and smoke generation, and flame spread. Therefore, the BIPV product need to be tested as well. However, there's no PV-specific test methods or enhanced performance requirements been laid out. So it has not yet addressed how these BIPV building materials need to be tested for fire behavior, flame spread, particularly when they are electrically active. They couldn't perform, they couldn't show different fire behavior. So smoke toxicity should not be underestimated as well, since gases of sulfur dioxide, hydrogen fluoride, hydrogen cyanide, VOC were detected from PET laminated PV fires. So another issue is also fire reactiveness of this BIPV products. So let's move on, and next slide, please. So following the reaction to fire requirement, you also need to check the resistance to fire requirement as building structures and elements. First, the resistance to fire originating from BIPV should be addressed in the BIPV designs. For example, solar wall cladding, since they can self-ignite, requirements for a barrier might be needed, particularly for BIPV claddings or curtain system to resist the fire spread, potential fire spread coming from the PV cladding itself. So this will be similar to the thermal barrier requirements currently in the International Building Code in the States, where a cladding system contains an insulation layer. Barrier is required to separate the cladding from the interior side of the building. So next, the resistance to fire exposure from within a building. Any cladding system mounted shall not affect the fire resistance of the primary exterior walls. This also applies to solar claddings. Now, in the case of solar, glass curtain walls are installed when a fire rating is required. The BIPV curtain wall shall be tested by the standard fire resistance wall test using the wall furnace. So some question could be those current, the failure criteria, temperature criteria, still applicable to BIPV. For example, temperature criteria, temperature rise should not be greater than 140 on the unexposed side. Since we know that during the normal operation, BIPV could be heated up and up to about 100 Celsius. So all those questions are still unanswered. And next, please. Resistance to fire spread on exterior of BIPV facade. Facade fires are big concerns, as we know. And we know that the smoke and flame can propagate rapidly via the cavity space behind the combustible claddings. In the case of BIPV facade, fire spread via cavities is also a concern. And this fire spread via cavity could be attributed to the PV operation temperature and the combustibility of PV and substrate layers and designs of mounting system. Usually cavity system for the BIPV could be designed for coolings of PV, the temperature coming from the normal operations. So for the vertical fire spread, the current local building codes require combustible claddings and curtain walls pass those large-scale facade fire tests like USS 134 or NFPA 285, exposing the BIPV products to window flame fire scenario, as you can see from these photos. So the question is still remaining, are these test methods and their test criteria are right for examining BIPV facade? Next, please. We have one more case in relation to the facade, fire safety requirements for BIPV DSF, double skin facade. Double skin facade is novel facade technologies, not only used in new building, but oftentimes to retrofit buildings, as you can see from these photos. So you can see the two skins. One, the exterior layer is a PV exterior glazing, which is installed outside of the primary normal glazings. Between these two skins, there'll be a plenum space in between. Currently, there's no detailed design requirements or codes available for PVDSF, and the fire risk of PVDSF are also not fully understood. Concerning a fire starting from a PV skin, the PVDSF should be designed for smoke and fire protection. This figure at the bottom slide here is from a modeling study conducted to investigate the smoke propagation through the plenum space. And the results are quite concerning, as you can see, because we observed significant smoke spread from the PV through the plenum space, potentially endangering occupant inside the buildings. So next slide. Conclusion here, the fire safety requirements and testing methods for BIPV as building elements, building structures are related back to the local building codes standard. Unfortunately, this current building code standards are developed only for the ordinary construction buildings, not for the BIPV products. Therefore, meeting the requirements in the current building codes or standard test method does not verify the fire safety of the BIPV products and systems. The current fire safety test and performance requirements should be re-evaluated in application to BIPV, since there's so many unique challenges posed by BIPV system. and it is necessary to develop requirements considering the actual burning behavior of PV module, particularly when they are electrically active in normal operations. New standard test methods or guides are necessary also for potential toxic smoke hazard, any additional fire protection system requirements for fire detection, fire suppression, and safe occupant evacuation. Also for firefighting considerations, including tactics, potential electrical shocks, and so on. So next, yeah, thank you so much. Contact me if you like to have more detailed information of the presentation that I made today. Thank you.
Thank you very much, Junko. Thank you. Thanks a lot. And we'll come back to you in the Q&A after the next presentation. So next up is Dirk Long from the Electric Power Research Institute in the US. So we stay in North America. And he's a researcher at EPRA working on safety of energy storage systems. So continuing on the conversation we just had with Victoria, I think you will take us into more details here. Thanks, Dirk, for joining us, and over to you.
Great, thank you. Glad to be with you all virtually today and to be speaking about the research that we're doing at EPRI on battery energy storage safety. A quick note about who EPRI is, if you're not familiar, it's the Electric Power Research Institute, and we do research work across the entire electric power industry. And specifically, I work within the energy storage group, supporting the electric utilities, predominantly in the US, but we also have quite a bit of work in other countries as well. And so we kind of serve as a bit of a not-for-profit R&D arm to a lot of the utility industry. So that's who EPRI is, and I have been doing battery energy storage safety research across many different industries. In the past 5 years, I've been working in stationary, which has some unique challenges, which I'll be talking about today. So glad to be here. I'll be talking about two trends that we see within the industry that were recognized about 18 months ago, which started this research project. And then I'll be talking about what the research project has been and kind of what we see as far as the landscape for energy storage safety right now. All right, see if the can. All right. So the first thing we've seen, which is not new news for anyone, is that there's a rapid increase in energy storage being deployed on the grid. So we are seeing that this is accelerating quickly, and the US Energy Storage Association has this prediction for 2030 with 100 gigawatts on the US grid. So even across the globe, we're seeing that being a very rapidly increasing area of technology deployment. And so when you have this much new technology being put on the grid, one of the ways that we look at this are how would these deployments be cost effective, available, reliable, safe. And really, when you look at these, safety and the reliability of it undergirds everything that you might hope that energy storage can do. And so it has a lot of benefit that it will serve on the grid for renewable energy integration and other resilience aspects. But if you can't rely on it, and if it's not safe, then it will be hard to deploy at the rate that we're anticipating it being deployed at. So we see this as one really strong current within the energy storage industry. And then following on, we're also seeing that there's a lot of system failures and large fire events happening within the built environment. And so these, we manage a database of public information about these events. And I'll put a link to this in the chat here. It's also, if these slides are available afterwards, you'll be able to look it up through there. But we manage this database, and we are noticing an increase in failure incidents that are happening across different integration types, different use cases. And so you have these two kind of converging trends that we recognized about 2 years ago with rapid deployment and failure events being seen. And so to address that and to kind of try to understand the landscape of safety a bit better, we started a two-phase research project where we are going to try to understand the safety landscape of energy storage and then sort of build out from there and look at how we might address it. And so we've just completed phase one, which is this portion on the left here, where we built a advisory committee of expert collaboration. Victoria Hutchinson, who was on earlier, was a part of that. And we also did site-specific hazard assessments where we did detailed safety reviews of 10 different energy storage facilities that had either been built in the last 5 years or were currently being built. And from that sort of top-down and bottoms-up approach, we've developed a strategic roadmap that really looks at the landscape of safety within the energy storage industry and sort of charts a path forward to effectively kind of increase the safety of these systems. And so one thing I want to reflect on is that EPRI is not unique in this. A lot of people have seen these trends and taken similar approaches. One of the very necessary ways to address these risks is through codes and standards. And those efforts are going well. So across the world, there's new standards being put in place for energy storage systems that really increase the safety of the systems built. But we also see that there's a time lag between when we recognize a problem and can get codes and standards implemented, and then further another time lag between the adoption of those codes and standards. And so one of the things that we're looking at is what are the ways that we can influence the safety of the system alongside those very necessary efforts through the codes and standards organizations. So we're engaged with codes and standards, but we're not writing them. We have kind of a parallel effort to kind of help in the interim environment here. And so to talk about what that looks like, I'll go through a bit of our strategic roadmap here, which is feeding into the phase 2 research that's starting today. This bubble chart here is our way of depicting the 22 topic areas that we identified as necessary areas of research and development within energy storage safety. So the size of the bubble indicates the potential impact on battery energy storage safety if you undertake that research. The vertical axis is the effort required to develop that resource, and the horizontal axis is the timeline at which you can achieve that goal. And so we've looked at this and we've identified these 22 topics, and I'll share a few of the specific ones that we've seen are particularly engaging that we're starting to work on. The first one that I'll talk about is this ST1 on the lower left. This is the common explosion hazard that lithium-ion systems have. So we've recognized that built systems still may have latent or unidentified explosion risks, and new systems really need to address explosion hazards effectively. So that's kind of an urgent special topic that we identified. The yellow circles are all response plan related. So when you've had an event, how do you, as the owner and operator, how do you address that? As the first responder, how do you prepare for it? How do you act on site? And so the yellow circles are different aspects of response planning that could use research and further resources. The blue circles are around technology development. So there's a category of topics here that really speak to the need for new technologies to be developed to address some of the safety concerns. That could be things in the suppression and mitigation side, or lowering the risk itself by developing cells, lithium-ion technologies that don't have the same fire hazards. And then the final one, which we see as really pragmatic and useful in the near term, is the green circles. These are the design tools. Within the current environment, while we're building a lot of systems across the world and codes and standards are just kind of catching up, there's a really pragmatic need for design tools to help us both adopt those codes and standards more effectively, but also use other industry best practice knowledge that is being developed kind of real time. And so that safety roadmap is a public document that we've developed. So I'll put a link to that in the chat as well. It's at the bottom of the screen here. So you can download that, and it kind of discusses these topics in more detail and kind of the approach that might be needed to address those different topics. The way that EPRI is going to start addressing these, so that roadmap isn't EPRI specific. There's things in there that EPRI can't do, such as developing new technologies that will be sitting more with kind of the technology vendors. But there's a lot of things that EPRI can do. And so the way that we're approaching this is what we're calling the Project Lifecycle Safety Toolkit. And what we're recognizing is that as we're developing systems and deploying these, there's a need for tools that can be used to increase the safety of systems at all the different aspects of the project lifecycle. Everything from what we now know about the battery off-gas plumes during a failure event. We've had some recent large-scale failures in the world that have shown the need for a better understanding around those plumes that come off during a failure. If you understand that well, then that can inform your planning and siting and system design to kind of mitigate the impacts of that. Again, I've mentioned explosions, and an example approach of how we've began to address some of the explosion hazards is that we kind of take this approach of identify, educate, and then enable. Identifying was this safety roadmap. We've identified these topics that we think are important to the industry. The second step is to educate. And so one public resource that we put out recently is this explosion hazards white paper. I'll also put that link in the chat of the Zoom, and then it's also on the slides for you get afterwards. But this is a white paper that really discusses the dynamics and necessity of understanding battery explosion hazards, more than just looking at what codes and standards say right now, but how do we understand that from a fundamental level and address it in systems both existing and yet to be built. And then the enable step is that we partnered with a research organization to develop a simple calculator to help kind of quantify at a first principles level what those explosion hazards might be in a system. If you said that one cell had a thermal runaway and vented, how much explosion hazard do you have then in that environment? And so that's sort of a design tool that helps step in the right direction, the first approach to these explosion hazards. And so we hope to take the same approach with lots of different hazards that are identified and kind of help the industry have the recognition of hazards and that first step towards safer systems in this gray area time while we're waiting for the industry to have safer technologies and better codes and standards and first responders that are more informed about the risks. There's a lot of really good work happening in all these areas, and it's converging on a future, maybe 5 years down the road here, where a lot of this will be resolved a bit better than it is now. But in that meantime, we hope to be able to kind of facilitate the industry with some of these resources along the way. And so real quick, then I wanted to mention this is our project that's doing that. It's called the Energy Storage Fire Prevention and Mitigation Project. And the way we structure it is that it's collaborative. So we want lots of people participating in that research. We had 15 different utilities in our first phase and a number of people across industry. And so that kind of helps us get better research. So that's the type of research that we're doing there. And then another thing I wanted to put up, this has a few more links in it for resources that we've already created, some of which are public and some of which are for purchase, but we're trying to create resources that are public facing that the industry can use to better inform the safety of these systems and create safe energy storage deployments over the next few years. And so with that's kind of my presentation. My contact information is here if there's questions after this, but I'm really glad to be able to participate.
Thank you. Very good. So we have a few more minutes for questions and answers. Maybe I can kick off with one to you, Dirk. Do you see the fire resistance of the materials used in battery casings, cables, electronics as significant? And I think that's important also for the audience here in the room as we are really dealing with fire safety of materials and how to improve the resistance to ignition of materials. How do you rate that in comparison to maybe other technological approaches or ideas? Yeah.
That's a very important part of this. And one of the things we've recognized with battery fires is that the battery cell itself is a very unique type of fire and requires very unique types of responses to it. But there's a lot of other components in the system that if we can make those less flammable and lower the fire risk within the greater environment, then we both can reduce the risk of those cell fires cascading and escalating into larger events, but we can also reduce the risk of more benign fires like a small electrical fire getting to the cells and causing a worse problem. So we've seen, for example, a terminal connection that wasn't clamped down tight enough, generating heat, and then the cable being what caught fire first, and then that propagating to the cells themselves. A cell fire is a much harder thing to deal with than a cable fire. And so materials that can help with the cable fire and other aspects of the system are a very important part of the landscape here.
Okay, thanks very much. Yeah. Yes, and maybe a related question to you, Junko. You showed us this on one chart. There was this breakdown of the different elements of PV systems. So we have the panel itself, but we also have the junction box and then the connectors and the cables and all that. Where in that do you see the most fire risk? Can that be pointed to certain elements, or where are kind of hotspots that also in terms of materials used could be improved or need improvement?
There's a few studies conducted with the collected information, collected incident reports, but those reports are old. But it says that 50% of the fire started from the PV system itself.
Okay.
Among all those many, causes. I think, each one has the equal contribution to the cause of fire. So not one specific, most significant cause of fire, but all those components need to be.
Okay.
Yeah.
Okay, thank you. Chris, do we have any questions come in?
There's a question in the chat. Is there a restriction to putting battery storage, for instance, in building basements? Are you working on the places where you can safely put battery storage?
Yeah, some of the more recent codes and standards have limitations to the amount of capacity that can be put in different environments. Those limitations depend on a lot of different things, and most of the codes also give an exception that can be taken if you conduct large-scale fire testing to show the safety of the system in that application. And so there's not a hard limit that I could say. For example, for a basement, it would depend on a bit more detail around the type of technology and the type of deployment, but there are limits defined in some of the standards. Up in the chat, it says which codes. So NFPA 855 has some of those limits for the US. Not sure off the top of my head for other regions, but those, there are limits, but then with better understanding of the specific technology safety through large scale fire testing, you can kind of get around those hard limits and get some more nuanced guidance.
Okay, thanks. Maybe also a quick question to you, Eric. Dirk, sorry. On your bubble chart, there was on the bottom left corner the explosion hazard, and it had rather low effort to prevent that or to improve that. That I found that a bit surprising. That it seems rather low effort to combat that.
Yeah. So specifically, the effort is to be able to address the hazard safely. What we found in the events that have had explosions is that the dynamics of the explosion aren't unusual, and the mitigating methods are well known and well established.
Okay.
What's critical is the understanding of when you have an explosion hazard, and then which direction of mitigation is appropriate. And so that's sort of a small amount of effort where we can characterize the explosions more safely or more effectively, and then be able to point towards the mitigations that will make them safe. And so it's pretty low hanging fruit. But if we don't do it, as we've seen in some of these recent explosions, it can be dramatic. So.
Okay, very good, thanks. Yeah. And maybe I'll lead over to our panel up here, Corinna Neumeister and Nino Maya-san. So what's your take also from also representing PINFA here and your companies and our specific interest or approach to this whole topic is materials, fire safety of materials. So how do you see this after listening to the presentations this afternoon? Maybe Corinna, if you want to start.
I think that we all know that industry is already doing a lot of research in improving also these type of materials, like, battery safety started with e-mobility and e-vehicles. So I think all the research which is being done there can also be transferred to energy storage systems in building stands. So a lot of research is going on. But my feeling is that, as also the speaker said, that the standards are missing in many cases, so that really also industry knows what exactly is needed. So I think we need a legal framework where we can orientate ourselves on, and then research can be more focused to get the real solutions for these type of new challenges.
Yes, Nino Maya-san.
Thank you for the very informative discussion today. So, as a material supplier, also our Asahi Kasei focusing on the new battery system and the PV system, and for example, today's the new regulation, upcoming regulation about low toxicity, for example, might be very informative for us how to make a direction for the new material development and new compounding and so on. And we believe these type of solutions should be developed as a material supplier for the new safety solution.
Mm. Yeah.
That's very critical information for the all material supply.
Mm. Okay, thank you. Yes, and I also think, also speaking for PINFA for us, the challenge, similar to what we are seeing in e-mobility, that also new requirements come up. We heard CTI, Comparative Tracking Index, this morning, is something rather new on being this prominent, and I also think fire safety within battery and battery materials is something rather new to us, but of course we're very open to work on that and also work with other stakeholders. And as said earlier, flame retardants are one element of the fire safety toolbox. Yeah? And there are other approaches to ensure fire safety, sprinklers in buildings, firewalls, and other approaches. But flame retardants have the benefit they make materials inherently more safe by increasing the amount of energy that you need to put into to get them on fire and to maintain the fire. So that's our approach to safety. And we hope we can also bring, in that sense, value to these new applications like photovoltaics in buildings and energy storage systems and the like. But I think, as we've seen in the presentations, still a lot of work remains to be done. If there are no further immediate questions, I'd like to invite Peter Mapleson to say the final word for this afternoon and for the conference. He's jogging on stage.
Thank you,
Over to
Adrian.
you, Peter. Thanks a lot.
Thank you. Thank you, Adrian, for organising this PINFA session. Thank you to PINFA in general. I think we had some very interesting discussions and presentations, particularly interesting for anybody who's got photovoltaic panels on their roof, which I have. So the first thing I'm going to do when I get home is rip off the panels and certainly not install an accumulator, or at least put it outside. But anyway, yeah, lots of things worthwhile thinking about, which frankly I hadn't done up until this point. So that's some interesting points there. I'm not going to summarize the whole thing all over again, so I will spare you that. Just to say, once again, thank you very much to our panelists and presenters this afternoon, and also from the rest of the day on this first day of the conference. And I will wrap up there just to say, once again, thank you to the various sponsors of the event. There is... just in case anybody was wondering, we had been planning to have a dinner this evening. That is not going to take place for various reasons, which I will leave you to work out for yourselves. So the evening is free for you, and I will see you back here, or at least Gunther will, maybe me too, at 9 o'clock tomorrow morning, when we have a session on investigating flame retardant mechanisms. And with that, I will say enjoy your evening and see you all again tomorrow.
Yes. Also, yeah. Also, thank you very much for the audience having joined online. Thank you for joining, and looking forward to see everyone again soon in person, hopefully. Thank you very much.